Alright, this is a made-up problem, and we're going to go easiest to hardest as far as the order that I do things in. This is combining power series, and so you have an expression like this, and they want you to give the power series for it. And all you're doing is looking at the main function, in this case sine. One of yours is exponential, logarithms, I don't know. But anyway, you will use an existing known power series, so we're going to be using that sine of x. And all I want to do is I want to just replace x with 2 of x, and then I want to multiply the whole thing by 5x squared. So this covers a lot of things, including the input to the function being a little bit different. You have stuff multiplied on the outside. Those are the things that they'll have you do, because you can't do much more than that. You can't be multiplying power series. You can replace the substitution, and you can multiply by powers of x only. That's pretty much what you're limited to, so we're going to do that. Anyway, sine of 2x right here is going to be the sum. K goes from 0 to infinity of, and I'm replacing x in this with 2x. So that's going to be right there. 2x. That's all I'm doing for handling sine of 2x. So I'm going to have -1 to the k, sum as k goes to 0 to infinity. I'm going to have 2x to the 2k plus 1 over 2k plus 1 factorial. That sine of 2x right there, again, just replacing x in your power series of sine of x with 2x. That exponent obviously applies to both the 2 and the x. What else I got here? Oh, and then the 5x squared, I'm going to multiply that in. Okay, so it's going to be 5x squared times that, and this is just a bunch of terms, an infinite number of terms, but 5x squared can be distributed to all of them, not literally going through infinity terms, but literally working with this generic term in the summation. So I do want to, what am I going to do here? I think I made it more complicated than it should be. I'm going to combine my powers of x, and my constants will be separate, my coefficients, so I do want to break up this 2x into 2 to the 2k plus 1 power times x to the 2k plus 1. It'll be an alternating series, so it'll still have that factor, it'll still have this denominator, 2k plus 1 factorial. None of that was affected by anything because all I did was replace x. I still have this on the outside. I'm not ready to distribute it yet, but I will be in a little bit. In fact, right now, I'm ready to distribute. So the 5 I'm going to combine with the 2 to the 2k plus 1 to get a part of my coefficient. The 5 is not raised to any power, though. That's just a single 5, and the 2 is raised to a power that's based on whatever term it is, based on the iterator k. 2k plus 1 factorial. It's alternating, so I still have this -1 to the k. And now my x's. So this is just going to be one coefficient. If I were to expand it out, I'd have some number times x to the 0 times some number plus x to the 1 times some number and so on. So this whole thing is my coefficient of the power series. I'm not figuring it out. I'm doing a generic summation representation of it. But I am going to multiply that 2k plus 1 from there, and then times an x squared, and those combine to give me a different power of x. So I'm going to go ahead and just erase and combine them. That's going to be adding. So it's going to be 2k plus 3. And I'm done. That's my power series representation of this. There's different things I could do to rewrite it in different forms, but I feel like that's pretty much the best I can do. But there's other situations where the form you write it in may not match up with the back, even though they're equivalent. So just be conscious of that. But anyway, that's the idea. Just working with an existing power series and plug substituting and then multiplying in powers of x and combining those powers of x in that way. That's combining. Alright, it's number 44. I'm doing a power series of g of x using f of x and using obviously differentiating and integrating. So we have to find a relationship between the two. One is the derivative of the other, one is the antiderivative of the other, or maybe, sorry, it might be two antiderivatives away. It might be a second derivative or something. We'll have to work that out in a bit. I also need, since I'm using this, I need to be able to find a power series representation of this. And note that this came after your combining because you will have to sort of do the reverse. You have to look at that and think what power series, that's a power series of what function, using sort of backwards of the combining. So one thing is if you have like 1 over 1 plus or minus something, you have to remember your geometric geometric series is x to the k, or yeah, which is 1 over 1 minus x. Is that right? Yeah, because it's a over 1 minus r, and that's your r. It converges when x is less than or 1. Okay, and k goes from 0 to infinity. Is that it? Yeah, okay, we're going to go with that. Okay, anyway, that's similar, except... How is that different? How do I get a plus there? Let's think about that. All right, I think I got it. I have to think about it for a little bit. This is not f of x, because I used another letter. I'm just going to call it a of x temporarily. Anyway, to get this, I would have to think of this as a of negative x squared. Using the combining, when I plug it into here, it would be 1 minus, and that's my x. So it'd be negative x squared, which will give me 1 over 1 plus x squared. Okay, this one is tricky, so I have to figure out that this power series is the power series of basically my geometric but in place of x, I'm putting negative x squared. Yeah, let me backtrack and make sure we understand it. Okay. Let me do this again. It's definitely going to be this, so I have to think about it. But anyway, I want to interpret this as a geometric series because it has that pattern. This is the series representation, and it equals this when when your r, because it's geometric, when your r is less than 1. So what I need to do is basically make it look like that. Let me do it a different way. So that's 1 minus, I need the minus because that's my geometric formula. Negative x squared is what I would have there. Yeah, this is better. Okay. So I'm kind of rewriting it and manipulating it a little bit to get it to look like 1 minus something on the bottom. That something is a negative x squared, and that means doing the combining thing. If I replace this with negative x squared, then this gets replaced with negative x squared, which is equal to what I have there. So the power series of this f is this one. This is the power series. That's the actual value. That's the power series, so it's negative x squared to the k. Which means that a lot of times when it's going to be alternating because of that negative inside with the k power. Alternating, they like to separate the negative 1 sometimes, and it's helpful, yeah. So that's it. That's my power series representation of f of x. And I did sort of the combining thing, but in reverse, and it was a little bit tricky. But anyway, I got it. I'm going to erase the work that I did to get there, so take a picture or look at it closely, and then move this up there because I need a lot of room potentially to work my problem. But that's one thing. You need to be able to express the f of x that they give you as a power series, using oftentimes combining power series, using known power series. And based on those problems that I saw, a lot of them use that, the geometric form, and just tweaking it a little bit. You have to be able to tweak it, as I just did. Okay. My next thing is I got to find a relationship between g of x and f of x. Using that form, I want to look at that and think about which one's a derivative of the other. Maybe there's some constants that you got to account for, but this is a negative 1 power of that denominator. That's negative 2 power, so when you do derivatives, you go from a negative 1 power to a negative 2 power. So I suspect that g of x is the derivative of f of x. I'll double check it. I'm going to work it through by looking at the derivative of f of x. Just old school quotient rule, or rewrite as a negative 1 power. We're not worried about series now. I'm just really just doing old school math 1 stuff. Let me see. So I'm going to rewrite that as a negative 1 power. I'll do my chain rule on it. The negative will come down. I'm going to have 1 over x squared to the negative 2 power, and then I'll have a 2x in there, or times 2x from the chain rule. Okay, let me rewrite it. It's going to be negative 2x over 1 plus x squared on the bottom. All right. You can obviously see the g of x in there. It's not exactly, but note that that is equal to, and let me start to summarize what I just did. I just did the derivative of f of x, and I got that, which is equal to, and now let me express it in terms of g. It's g except with that negative 2, so this is just negative 2 times g of x. That's the relationship between the f of x and the g of x that they gave me. Okay, yeah, I'm good. I'm going to erase the work that I did to get there and move this up there because that's an important thing that I need to keep, but I don't need the work and I need the space. So take a picture. Too late. I want to express g of x in a power series form. So actually I'm going to go one more step here, but I'm going to put it up here. I'm just going to divide by the negative 2. So I'm going to note that g of x, because I'm looking for an expression with that, and I want to relate it to a derivative or an integral of f of x with some coefficients floating around, and that negative 2 is one of the coefficients floating around. So g of x is going to be negative 1/2 times the derivative of f of x. That's it. Me just working a kind of recognizing that when I do the derivative of that, it'll go 1 power down, and it'll give me something close to g of x, you know, with a little tweaking. And working it out, and that's a relationship. The relationship between g and f, one being the derivative, or multiple of the derivative of the other, or the antiderivative of the other. I also needed the power series representation of f of x, and that required me to tweak the geometric series formula. And now I'm ready to do the main thing, which is to start with f of x in the power series and do differentiating term by term. So let me start putting in here. Negative 1/2. The derivative of, this is g of x. G of x is equal to, it's obviously equal to that, but I'm doing a power series representation by writing it as negative 1/2 times the derivative of f of x. And f of x is given by this power series here. Negative 1 to the k, x to the 2k. Wait, sorry, there's nothing underneath it. What am I doing? Okay, and now I'm going to do the derivative with respect to x term by term, so I'm just going to work on these. One thing to note is that if I were to expand this, it would be 0 power would be 1, would be my first term. Next term, k is equal to 1, would be a negative x squared. Third term would be, I don't know, who cares, but my main thing is when I do the derivative of this term by term, it's going to be the power rule on every single term. Well, let me write one more term. It's going to be plus, where am I? K is equal to 2. It'll be positive, and it'll be x to the 4th. Okay, and then minus something. What I want to be doing, I'm going to write it in expand form just to talk about what's happening. We're not doing it that way. So that's what I'd be looking at if I expanded it out and I did it term by term. And I'm just going to be taking the derivative, the power rule for each of these. But be aware the derivative of the one is any constant, and the constant term will be 0. So you're going to lose that constant term. I'm going to talk about that because that's the thing you have to account for when you do this. But let me go back to, I'll leave that up. I'm skipping this though. This is just sort of mentally thinking what we're doing. But I'm going to go back to working with this. I'm going to apply the differential operator or do the derivative of this. It's with respect to x, so everything else is constants. The k's, the negative 1s, any other numbers floating around. Just the x to that power, and I'm doing a power rule on it. So it's going to be x to the, I got to drop that power down by, I got to bring the power down, sorry. Bring the power down, and then reduce the power by 1. So that's a power rule on this x to the 2k. 2k comes down. Minus 1 from the exponent, and that's doing a derivative. Keep in mind what else I got. I got that negative 1 to the k. I'll have this negative 1/2 out there, and I'm good. Except that when I lose if I put 0 here, what's going to happen is when I expand this out, I'm going to have I guess I'll just have 0. But sometimes you have an issue of this would be x to the negative 1 power. And it can create issues where it's not accurate. So what they want you to do is generally just know that because the constant term was the 0 power, you just lose it. So they'll change that to 1 in the sense that you just lost the constant term, the k is equal to 0 term, because it turned to 0 when you took a derivative. So that's what happens when it goes k0 to k1 when you do that derivative. Anyway, what am I doing now? I'm going to multiply that in, and I'm pretty much good. Be aware, I'm going to, yeah, I guess, okay, I'm going to work out slowly. The negative 1/2 times that 2, the 2's cancel. That's just a regular 2, that's not to any power. That's just a regular 2, not to any power. They're going to cancel. I'll have a negative 1 left over. So I'll just have a negative 1 left over when I multiply those. And I can now combine these negative 1's. So my final answer will be negative 1 to the k plus 1. X to the 2k minus 1. And that's it. That's how you have to work it out. The main thing is you get this relationship between g and f of x. Put that on your form and you're going to work with that. Isolate the one you're trying to do, g of x, move things around, express g in terms of a derivative or antiderivative of x with some constants floating around, or maybe even powers of x like that other combining one, and then just do what you got to do, working that. You'd be a derivative term by term. You got to worry about taking the derivative of it and losing that constant term. There's another issue when you do the antiderivative of getting the plus c, the constant of integration, and handling that. I don't know how much she's going to throw at you, and I don't want to do it if it's not going to come up. So let me know if you need to talk about the plus c coming up in a problem that she assigned. Anyway, that's it. Okay. I am going to... Wait, is this going to work? I gotta think about this. Anyway, let me see if it works out. I made this problem up. I wanted to keep it simpler than what you're going to be dealing with, just to make sure you understand the overview of it. I don't think I can do this. Can I? Let's see. Okay. All right. I feel like, okay. Let me work this out, and if it doesn't work, I got to redo the whole thing, but I'm going to see if it works the way I thought. I just did it off the top of my head, and now I'm questioning it. Okay, so a couple of things we need to remember. We need to be able to recognize some series that diverge or converge. 1 over k is our harmonic series. It'll diverge by the p series with p is equal to 1. With a negative 1 there, where it's alternating the same series, but in alternating, it actually converges by the alternating series test. Is this thing on? Yeah, we're good. And then the ratio test or the root test is very similar, but you do a limit. You get an L, and basically if that L is less than 1, it converges, greater than 1, it diverges. Or if it's inconclusive, if L is equal to 1, it's inconclusive. So those 3 scenarios are all relevant. So let's start working this out. We're going to do the ratio. So before we even get to the ratio test, the idea is this is not an actual series because you have an unknown x. And if I set x to be 1, no, sorry, if I set x to be 4, what's going to happen is this series boils down to, I'm going to replace x with 4. It's going to be 4 minus 3, which is 1 to the k over k. It doesn't matter whether I start this at 1 or 2. I only started at 1 because I can't have 0 on the bottom, but it doesn't matter. You can start at 5. It doesn't matter. The convergence or divergence is purely based on the end behavior. So where the iterator starts is irrelevant. So a lot of times when it's irrelevant, you don't even bother writing it. It's just an infinite series, and we're looking for convergence or divergence, so the first 5 terms won't even matter. All right. Anyway, one more time. For x is equal to 4. I plug in the 4 there. I actually work it out. That becomes 1 to the k, which is just 1, and I get 1 over k, and I get the harmonic series. So it diverges there. It diverges when x is equal to 4, and I did figure that out by just plugging in 4. For x is equal to 2, I would plug in 2 there. And leaves you with a negative 1 in the parentheses, to the k over k. And knowing that that's now alternating, I know it's converging by alternating a series test. So this series right here, this power series, diverges when x is 4. When we replace x with 4, it converges when x is equal to 3. And so the idea is different values of x will end up with different behavior. This will converge for some values of x. It'll diverge for others. And we shouldn't have any inconclusives. We should be able to conclusively determine whether it converges or diverges for any x. But we don't want to just do it one by one and just try different values, so we have to tackle them all at once. And the way we're going to do that is working the ratio test, leaving x as unknown until the very end when we deal with the L. Our L will have an x involved, and then we'll be looking at these 3 scenarios. So that's the idea. It'll converge for different values of x. It'll diverge for different values of x. Let's start working it out. Okay, let me do the ratio test. I'm doing a limit as k goes to infinity. I'm going to take k plus 1 term, put it over the k term. Obviously, there's a lot of cancellation here. So, and if you know how it's going to work, you can flip it ahead of time. So, but let me go ahead. And what you want to do is you want to stack the things that are like the same, coming from the same factor. You put them on top of each other in an appropriate way. The k and the k plus 1 are coming from the same thing. They end up being flipped. Okay, and oh, I'm sorry, sloppy there, because I need limit as k goes to infinity. Okay. I can do piece by piece. I want to simplify first. This one obviously simplifies to just an x. One is, the absolute value is actually relevant here. It's always relevant, but it's particularly important here. The ratio test requires the absolute value of that ratio of the k plus 1 term over the k term. So when I combine these, it's just subtracting powers. K plus 1 minus k is 1. So I end up with just x minus 3. Times, and the k over k plus 1, technically that's in the absolute value, but we're only dealing with positive k's anyway, so I can pull that out because I know it's positive anyway. This, not so much. This could be, x could be 2 and get a negative, and so you'd have to worry about that. That stays in the absolute value. That can in theory be pulled out because it's just positive k's anyway, but keep in mind I'm still doing the limit as k goes to infinity. Now, it doesn't always happen, but this particular factor, there is no k, they cancel it out, and I just kept this. This is unrelated to the limit as k goes to infinity, so the limit here only really applies to that. And you got to remember your rules, so you got to be able to do it quickly. Same power, this goes to 1. This whole limit goes to 1 as k goes to infinity because it's the same power terms on top and bottom, the same degree. Or you can do L'Hopital's rule, and it's going to be 1 over 1. Either way, the limit of that as k goes to infinity is 1. And this is just a factor that can be pulled out of that. So my actual limit is the absolute value of x minus 3. I don't have an actual value that I can work with yet, but I do know this is my L. This is my L in the ratio test. And now I can sort of break down when it's going to when the original series is going to converge. When this L is less than 1, I know it's going to diverge. When this L is greater than 1, it's going to be inconclusive. When that L is equal to 1, and I'll handle that, but separately, case by case. So let's summarize. I'm going to erase over there. This is my limit when I get the ratio test. It has an unknown x, but now I can use the properties of the ratio test. So my original series, it'll converge when L is less than 1. That original series will diverge when this L, the limit of my ratio test, is greater than 1. And it'll be inconclusive when that x minus 3 is equal to 1. Okay, and now we got to work with absolute values. It's not a huge deal, but they tend to focus on the converging. So the idea is they don't work with all three. We'll talk about how all three are related, but they just work with the convergence one. And they start solving this. So if the absolute value is less than some positive value, that means the x minus 3 has to be between -1 and 1. And then I can add 3 to all three sides, so it's going to be 2 and 4. Is that right? Add 3. Yeah. Okay. 2 to 4. And this is this is a converging one. It converges when that limit to L is less than 1. I worked it out, and that means it converges for all the x values between 2 and 4. I'm going to erase. Nah, I can fit it here. So graphically, here's my number line, and notice the x minus 3 is relevant because that means that's a sort of the center of the interval of convergence, basically that minus 3. So it's like the whole thing shifted to 3 as a center, and I know that it's going to converge between 2 and 4. And that's my interval of convergence, and the radius, it's like, you start at 3 and you draw like a circle and it has a radius of, it's a radius of half that interval length, so the radius is 1. The radius of convergence. However, we're not quite done, and so let me summarize. It converges within there because any value within there will make that value less than 1. It will diverge above 4 and below 2, because any of those values below 2 or above 4 will make that limit, that x minus 3 limit, greater than 1. So I know it's going to diverge outside. In fact, they don't even work with that because they know if it converges within here and that's your interval, everywhere outside it diverges. But it's inconclusive at that point and that point. As of now, it's inconclusive because 2 and 4 will make it equal to 1, and that's where that limit is inconclusive. So these are inconclusives as of now. So I got more work to do, but not much more, and I'm going to erase this because this is done. Right now my answer is going to be the interval of convergence and the radius of convergence. I can start to write my answer. I wouldn't normally start writing it out now, but I do want to summarize what we found so far. The radius of convergence 1, that's at half that interval. And then my interval of convergence is going to be 2 to 4. The only question is, am I going to put a bracket there or parentheses there, or bracket or parentheses, because I don't know what's happening at the endpoints. But as of now, let me go ahead and just sort of like, I don't know what I'm going to put there yet. But I know it's going to be 2 to 4, either including one endpoint but not the other, or maybe including both or whatever. Sorry, I don't like those blobs. Well, I do like those blobs, but I want to put them in red as something that needs to be addressed still. Okay, how are we going to determine what's happening at these inconclusive endpoints? We're going to check it manually. In fact, I did it earlier, but let's pretend I didn't do it earlier and let's work it out. I'm literally going to look at what happens when x is 2, because that's a question mark, inconclusive. And I'm going to plug in 2 in for x, and I'm going to get -1 to, well, let me write it out so you can see your notes. I'm going to do x is equal to 2 minus 3 to the k over k. That's going to be a -1 to the k. It's an alternating harmonic series, and that converges by the alternating series test. So when I start drawing where it converges. I'm going to do like a shading of an interval where it converges everywhere between, and 2 is going to be included because it converges there. Let me check the other endpoint manually. For x is equal to 4. I'm going to plug in the 4 in for x here. I'm going to get a positive 1 to the k, which is just k. Sorry. Positive 1 to the k is just 1. So I end up with the actual harmonic series, which diverges, because I know that's a p-series with p is equal to 1. It diverges by p-series or harmonic series or whatever justification you like. So it diverges there. That's not included into my interval convergence. That hollow circle will stay open, but I can now write out my thing. It's going to be bracket, because 2 is included. It's going to be parentheses because 4 is not included, and I could write it out as x like that. I could give it like that as well. Anyway, that's it. You just do your ratio tests, getting your limit for the ratio test of L as an expression involving x, and you are literally working out the 3 scenarios, but just focusing on the first scenario, knowing that it'll converge here in this interval, it'll diverge outside of that interval, and the endpoints you have to check manually because they'll be inconclusive at those endpoints. That's it. That's how you're finding the interval convergence of a series. All right, best of luck to you.